So we have one more speaker before our break. And the speaker is Dr. Yan Gao, that obtained his PhD from the Machine Learning System Lab this year of the University of Cambridge. And his interests in terms of research are in machine learning, deep learning, and optimization. And he will talk about federated self-supervised speech representation learning. So Yan Gao, if you want to hopefully unmute yourself if we have allowed you to do so.
Yeah, can you hear me?
Yeah. Yes, we can. And we can see the slides as well.
Okay, great. Yeah, many thanks, Tito, for the introduction. And yeah, but I haven't officially got the doctor title because I just waiting for the defense. Yeah, so far, yeah. But yeah, this is just a update for my pro. So I've submitted my thesis. So I'm currently doing a postdoc in the same lab, the Cambridge Machine Learning System Lab. Yeah, so let's start. So we will look into the topic of federated self-supervised learning for speech. So obviously, so it's a combination of the federated learning and also the self-supervised learning. So I know you may not familiar with one of them or both. So to better understand the topic, let's just break down it and introduce them separately. So yeah. So first, so what's speech self-supervised learning? So let's ask ChatGPT. So we may not always get the correct answer from it, but this time it looks fine. So let's just take a look. So yeah, self-supervised learning is a form of unsupervised learning, and this means we don't need labels for the training, and instead we generate the labels from the data itself and design the task that the model can then use for representations from this process. And when applied to the speech data, the speech self-supervised learning focuses on using the large amount of unlabeled audio data to learn the repetitions that then be used for the various downstream tasks. So basically, the core idea, so the self-supervised learning for speech or whatever other type of data basically involve two stages. So at the first stage, the encoder of the self-supervised model, the SSL model, extracts the self-supervised features from the unlabeled audio data. And then the pseudo labels are generated based on the specific SSL objectives, so which could be used to calculate the SSL loss and update the model weights. And at the second stage, the pre-trained SSL encoder can be used to solve the downstream task by adding a downstream model on the top. And during this fine-tuning process, the SSL encoder can be frozen or not based on the requirements. And for the speech related downstream tasks, I think it involves almost all of the common tasks like the speech recognition, the keyword spotting, emotion recognition, speaker identification, and so on. And in practice, the study of speech self-supervised learning has gained much attention in recent years. So this figure just shows the number of occurrences of self-supervised concepts at the Interspeech conference over the last 5 years. And obviously, the research related to this topic become extremely active in the last year, right? And so why, what's the reason? The reason why this topic is so expensive, is so popular, is that it's really work well on the different downstream tasks. So if you look to this table compared to the traditional features like the F-bank, you can see the large-scale SSL model have got a new state-of-art performance on the various downstream tasks, right? But also the SSL performs well on the speech and audio data. On the other hand, these type of models are huge with the hundreds of millions parameters, and also they're hard to train and are resource intensive. So for example, to gain a state-of-art performance with the Wave-2 model, you have to burn your GPUs for thousands of hours. Indeed, this is not good for our environments, right? Yeah. Okay, so next, let's see the federated learning. So by asking the ChatGPT again, so we can know that the federated learning is a form of distributed machine learning scheme, and where the training data remain on the devices. So this approach is developed to address the privacy and also the security concerns of sending the raw data to a centralized server. And a typical FL procedure has the following steps. So first is a global model is initialized on the server and all devices. So here we call them clients are connected, and then a fraction of clients are chosen, and they receive a copy of the global model. And the client start to perform the local training using their own data, and then send the updated model to the centralized server. And on the server, a new global model is generated by aggregating the client updates. So this process is repeated for a number of rounds until the model conversion. Yeah, so during this FL training, you see that the user data is always stored locally, so which will reduce the risk of data breaches or the misuse, right? And unlike centralized training, there's more constraints when training the model on device. So the core challenges of federated learning are divided into 4 aspects. So first, in the real world federated setting with a number of devices, the communication between the devices and the server is slow due to the limited resources. For example, the bandwidth, the energy, and the power. And second, the storage and also the computational and communication ability of each edge device in the federated system may differ due to their device hardware situations, right? And yeah, and third, so the distribution of the data, the user data will be very non-ID, so it's independent, identically distributed. So this would cause issues for the training. And the last point, so as a main concern in the FL, the federated learning, the privacy could be protected by only sharing the model updates instead of the raw data in the training process. However, the user's sensitive information may still be revised, be revealed during the communication, between the edge device and the server. Yeah. So, okay, so after understanding the main characteristics of the self-supervised learning and also the federated learning, let's go back to the original topic, federated self-supervised learning for speech. So why do we want to combine these 2 concepts, and what benefits can we get if we combine them? So actually, so FL and SSL have many complementary features. So for example, FL can offer almost infinite data from the user side, right? And while the SSL benefits from the large-scale data training, so it matches. And also the user data is almost unlabeled, and the SSL, on the other hand, doesn't require the labeled data for training. Yeah, and as for the privacy, so we can't say FL offer privacy guarantee, but indeed it reduces the risk of data breaches and also provides the opportunity to make use of the user data for SSL model training. And at the last point, FL has millions of devices and which may jointly provide large compute capabilities required for SSL, right? So as a result, combining SSL and FL feels natural. Okay, so we already know we have a big motivation to combine them. So next, let's talk about the feasibility of doing this. So we actually have several concerns here. So for example, from the hardware aspect, the FL devices, its edge devices may not afford the large SSL model training, as these devices only have the limited computational capability and memory. And also from the algorithm aspect, the no-ID data and also the heterogeneous data availability in FL may destroy the SSL training. Yeah, so okay, to investigate the feasibility of the speech federated self-supervised learning, we can set up some experiments. So here we use the week-to-week 2 model. So both is base and large version to run some benchmarks. And for the data set, we choose a common voice Italy set, as it's relatively small, right? So which contains 370 hours speech data with average sentence length of 5.5 seconds. And then we select several devices for the benchmark. So we choose the A40 GPU represents the centralized training. And as for the edge devices, we use like the MacBook Pro, the Raspberry Pi, and Jetson XPhil NX and AGX. And we also consider different the mobile processors for the memory comparison, including the Snapdragon 870, A15 Bionic, and Google Tensor. So okay, so we first conduct an investigation about the bottlenecks that cause the SSL model to be expensive to train. And to do this, so we break down the week-to-week model into 3 modules, so which are the CNN, the transformer blocks, and the quantization modules. So this table shows the numbers of the parameters and the flops for each of the 3 modules in week-to-week 2, and given input audio of duration 5.5 seconds. Yeah, so if you look at this table, immediate observation is that the transformer block is the heaviest module compared to the rest, right? But this first order analysis doesn't consider the training dynamics, and therefore a more in-depth look into the impact of each sub-architectural module is needed to identify the bottlenecks. So next step, we conduct a per layer breakdown of the base model in terms of its memory and compute. So it's training with input of length is still 5.5 seconds with batch size 4. So this figure, each bar represents 1 layer, and it's starting from the first layer to the last one over the x-axis. And we see that at the end of the forward path of the memory cost, right? If you see the left figure, the memory cost is at its maximum, so it's shown with the red cross in the figure, right? And an interesting observation is you see that the high memory utilization and compute needed for the CNN encoder stands out compared to the rest of the model. And this mainly due to the consideration of the size of the input tensor passed through the layers. yeah, so okay, now we have known the bottleneck of the SSL model, and let's just put it into the FL environments. So let's first say the memory consumption. So this figure shows the memory consumption of training wave-to-wave to base and a large model on different lengths of input sequences. And the typical FL devices like the Jetson Xsphere AX or Raspberry Pi have only 8 GB memory. And yeah, and you see them in this figure, you can see the lower horizontal dashed line, which is 8 GB line. And also some more powerful devices like the Jackson Xsphere AGX or the Snapdragon 870 has 16 GB memory, so it's showing on upper dash line. Yeah, so we can see that the device with 8 GB can only train the base model, while the devices with 16 GB can train the large model with the sequences of 7 to 8 seconds at most. But however, if longer sentence, for example, 15 seconds are considered, as is, it's typically the case with the current SSL model. All the devices could only be able to train the base model or even none of them. And another interesting is that you see the sequence length can link to the different type of offline speech applications. So that could be regarded as a downstream task for the pre-trained SSL model. So for example, the keyword spotting may only require the short sequences, while the speech recognition may increase this to much longer sentences. Yeah, but however, the current released SSL model use more than 15 seconds sequences, which make it impractical to train the SSL model on the FL devices. Yeah. Okay. So as for the training time, so this table shows training time. So is the average seconds per batch of the wave-to-wave model using the sequence with average length of 5.5 seconds. And the OOM here stands for out of memory. Yeah, so obviously you see the FL devices are dramatically slower than the GPU. For example, the worst case, the Raspberry Pi is around 200 times slower. And the use of mixed procedure can provide a boost in the training speed for the devices, but the support for the mixed procedure training is currently rare in the embedded devices. So if we consider a full FL training, the A40 GPU would take around, I don't know, three days to finish the whole training. If you train on the common voice Italy data set, and then the FL devices would take like weeks or even months to finish the training. So as a result, the current large-scale SSL model training are simply impractical for the current state of the real-world FL environments. Yeah. On the other hand, so what if we just ignore the hardware constraints and run the SSL training in FL with a current version of algorithm? So let's set up another experiment. Yeah. So here we still use the same model, the VIC2 base model and the common voice Italy data set. And for the FL potentials, we have two settings, the 10 client settings and 100 client setting. And we investigate two aggregate methods, the Fed average and the loss-based aggregation. So the Fed average so weighs the client's model weights based on the number of samples so during the aggregation, and the loss-based aggregation with the client's models based on the average training loss of the each client. Yeah, and as for the downstream task, we choose ASR and add 3 layer lines on the top of the SSL model. Yeah, so let's see the results. So we see that all the the federated SSL representations provide a competitive performance in both FL scenarios compared to the centralized setting. So this demonstrates that the feasibility of training SSL model in FL if the hardware is unconstrained. And also, you see that the loss-based aggregation achieve lower word error rates in both FL setting, so which indicates that the weakening the effect of low-quality clients can help the aggregation process in the federated SSL. Yeah. So overall, so based on our analysis, the hardware constraints becomes a bottleneck of training speech SSL model in FL. Hence, we need to think about how to solve these issues, right? So of course, like a more efficient SSL method is required, and also, for example, the better aggregation strategies are also needed to speed up the SSL model convergence. So it's still a long way to go. Yeah, so please come and innovate with us. And you also you must curious about implementation about the speech federated self-supervised learning. So it's easier to facilitate the simulation of the speech federated SSL by integrate the speech brain with Flavor. So Flavor is a friendly FL framework. Yeah, and for more details, you can just look into the tutorials, yeah, which is on the speech brain website. Yeah, that's it. And thank you for listening. Any questions?
Right, thank you for the presentation. So I think we have, so let me turn my camera on again. Yeah, I think we have one question in the chat, so I need to scroll back a bit because there have been a bit of discussion. Okay, so in FL, so this is from Gérard Chollet. In FL, how could we control the quality of the data provided by the clients? So that's the first part of the question. And the second part is, what will happen if some clients inject voluntarily invalid data?
Okay, for the first question, I think one method would be we can design a smarter aggregation strategy to screen the low quality data. For example, the one I used, like the loss-based aggregation method, which could give the different ways to the clients based on the training loss. So for example, if the loss is lower, that means it may due to the low quality data in that client. So that's just give it a lower weight when doing the aggregation. Yeah, so this is one potential solution for that. So sorry, what's the second question? I forgot that.
Yeah. It is, what will happen if some clients inject voluntarily invalid data? So I guess it's like some adversarial I don't know, maybe something that is super noisy without speech, for instance, in the case of SSL. So what happens if some of the data is really wrong in the SSL?
Yeah, I think it's also you can consider that like a low quality clients, right? If it's some noise from the user. Yeah, and for that question, I guess that the similar solution would be a better aggregation strategy, and yeah, also when doing the federated learning, when in each federated round, we would select a certain number of clients, and during that process, maybe we can set up evaluation part. So we can just from that we can screen some low quality clients, and just keep the the better clients for the training. Yeah.
Okay, so we have two more. Let's pick the first one, which is from Jarod Duré. Do you think that hardware advancements such as the introduction of NPUs designed for mobile and low-powered devices will overcome the limitations of computational capabilities for training SSL models using FL?
Yeah, I see. The hardware is always developing over time. So I think from the current trends, I say it's hard to go to the state of art performance when doing the training the SSL model in FL, because even in the centralized setting, it's hard for us to get a state of art performance using the modernist GPU. So yeah, the MPU is good, but I don't think it's powerful enough to get the state of art performance. But yeah.
Okay, and last one, I guess it's connected then, because it goes from the data perspective. It's from Salah Zayem. Current main SSL models are relying mainly on clean, generally read data sets, such as LibreSpeech and LibreLite. Federated learning data is supposed to be less cleaner. How much do you think it's beneficial or not for the SSL representations that are learned with this?
Yeah, right. So I think that's I know it's hard to get better performance if the data is noise. For example, in the real world, we need if the data from the real users is indeed will be much noisy. But I think first of all, for example, if we want to do the downstream task like the ASR, the speech recognition, maybe the SSL would be help to at the first stage to learn some representations from the noise data. I think the SSL model is more robust to deal with the noise data than you directly using ASR supervised model. So maybe the SSL if we integrate the SSL in FL, it's maybe get better the representations, and then using that for the downstream task. For example, the ASR will be got some benefits from SSL for this specific task. Yeah.
Okay, so there is a last one, but we are running out of time. So please feel free to answer this question in the chat directly.
There is the break now, so we can stay like a few minutes more if you have questions.
Yeah, sure. I mean, we can. Yeah, that's true. That's
move on, maybe one or maximum two questions, and then we can really take the break.
So that's from Pavel. Sorry if I might mispronounce your name, Sirta. Do you think representation can be also speaker independent? Is this an issue for security?
Yeah, I think it could be speaker independent, but so if you so FL can't give a privacy guarantee, as I've mentioned. So it's even the length representations or the model weight could be rolled back to some useful information. is the sensitive for the certain users. So if you consider the security or privacy, we need like more techniques to solve this problem. Actually, it's the increase the privacy in FL is one branch of the research in FL area. So, for example, like the differential privacy or something, a similar technique could adding the noise or some to make the model with which could be give it more privacy and more security when doing before doing the aggregation on the server. Yeah.
I have a question, actually, clarification question. Could you maybe please clarify which part of the systems are implemented with SpeechBrain and which parts are implemented with Flower? Can imagine, but maybe you can disclose better.
Sorry, which part is
which part is implemented with SpeechBrain and which part is Flower?
Okay, so since it's like that, so in the so we use Flower as a FL framework. So in that framework, we have a client class, so it could provide the training function. So in that function of that client class, we replace the training function by the original one with the SpeechBrain training recipe. We have a specific train script for the training. So we just replace that with its own training script in the SpeechBrain. So that's the main modification when doing the integration.
Thank you.
Okay. Thank you again for the presentation, Jan. I think it's now time for the break. We have now 24 minutes. So we will be back in 24 minutes, and it will be, I think we are starting with, if I'm not mistaken, the SpeechBrain roadmap and the latest updates from SpeechBrain. So if you are eager to know what will change, what we have to announce, some pretty big things, then, well, just join us again in 24 minutes. So
it'll be really great this afternoon, right? So we have many interesting things.
Yeah, I mean, the whole afternoon is, of course, interesting.
the roadmaps and also the talks and also the panel, which will be super great, I hope, because there are many interesting people. All right.
See you.
See you there.